Let's try to understand the ionic bonding a little bit better, and we can use different kind of models that you may already be familiar with. In this case, we're just going to talk about how the lithium fluoride ionic bonding is formed. From the electronic configuration point of view, you can think of that lithium is just one electron away from configuration of noble gas, helium, so it would rather lose one electron, and fluorine is one electron away from gaining one electron and gaining the electronic configuration of noble gas again. This is why there will be a transfer of electrons from here to here, and what you will see in terms of electronic configuration is that now lithium is a 1s2 full shell, and fluoride is also 1s2, 2s2, 2p6. It's a full shell again. This same representation can be shown in boxes. I think it's pretty straightforward to see, and hopefully you're already familiar with the Lewis model or the Lewis structure, in which all of both lithium and fluoride now, fluorine is the atom, fluoride is the ion. So both of them, when they form lithium fluoride, they follow the octet rule. So you can always count. It's not true. Fluoride follows the octet rule, lithium does not, it only has 2 electrons. So apply the octet rule only to the second period of elements. So octet rule, take home message, octet rule only second period. The first period, third period do not necessarily need to follow the octet rule, and we will see many exceptions. Okay, of course in organic chemistry, being carbon, hydrogen, oxygen, those have to follow the octet rule. Let's try to understand the ionic bonding from a quantitative point of view. The question is, how can we predict how strong the ionic bonding is depending on what ions is made out of? We want to have an estimation of how strongly attached the cation and the anion are in the ionic lattice. Well, a very simplistic view and yet useful is applying the Coulomb's law, or the electrostatic energy model that you have seen before, in which the energy is proportional, let's say it's proportional to the product of charges, charge 1, charge 2, divided by the distance among them. In this case, charge 1 and charge 2 is the cation and the anion. This says that the higher the charge, the higher the energy, and the stronger the bond. The higher the charge, the stronger your bond is. And in the distance among charges, we're going to do is to add the cation radius and the anion radius. That means that the larger the size of your charge, the weaker the bond will be. Okay, so you want, for a strong ionic bonding, you want highly charged ions, -2 + 2, -3 + 3, and small ions. Okay. So here's some examples. If you compare the energy lattice of, the lattice energy of the chloride ionic compounds going through the first column of the periodic table, you see that lithium, you may well remember that lithium is smaller than sodium, this one is smaller than potassium, this one is smaller than cesium. How is that reflected in the lattice energy? The larger the atom is, in this case cesium chloride, the smaller, or I should say, the more positive the energy is. That is weak. This is a weak bond, and this will be a strong bond. So this model correlates with the size of the cation. Hopefully that makes some sense. Let's look at any possible combinations of cations and anions. Well, look at when we try to understand how negative or how strong the energy interacting in the lattice is, the largest number is, of course, the smallest of the both cations and anions. And the smallest of the energy, the smallest of the attraction, is when you mix the largest of the cation in this series with the largest of the anion. So this model, as simple as it may be, it helps us predict some of the basic trends. Okay, so take home message, what we already said: the bigger the anions that the cations are, the smaller the ionic bonding energy is. Uh, Remember that it's a negative number, so they should say the larger, but so let's say that the weaker the weaker the 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 energy, the weaker the energy, or the lattice. Okay, so and of course, the higher the charge, the higher the energy, or the stronger the bond will be. Let's see if that makes some sense when we apply it to a problem. In this case, it's asking you to decrease an ionic lattice. I should say energy lattice, listing decreasing ionic energy lattice. So that is, you have to identify which of these four compounds we're looking for the size, and we're looking for the charge. Notice when we look at this model is that the charge factor, just if you have a 2 here instead of a 1, you will multiply the energy by a factor of 2. So typically it's safe to say that the charge effect will have a stronger effect than the size effect. So in this case, for example, what are the charges? We have strontium oxide. Strontium is the second column, oxygen is the third, is a 2 negative, and calcium oxide. So the charges are the same. Which one is smaller? If you go to the periodic table, you will see that calcium is above the periodic table than strontium. This means that the energy, the lattice energy of calcium oxide, and I'm going to put in absolute terms because it's negative, is larger than the lattice energy of strontium oxide. Okay, and among the other charges, calcium chloride is a positive and a negative, and calcium bromide is a positive and a negative. So potassium, I've been saying calcium, I apologize. This is potassium bromide and this is potassium chloride. Being both potassium, what will make the difference is the size of chloride and bromide. Chloride is smaller, so we will say that, and we will continue here, that the energy, the lattice energy of potassium chloride will be larger than the lattice energy of potassium bromide. Again, there's no way for you to quantify why it is that the charge 2 has more effect. Just think about it. If you have 2 and 2, you will have a factor of 4 in the denominator. In here you have 1 and 1, you will have a factor of 1 in the numerator. So this means that the energy, the radius would have to be 4 times bigger, which is not in the case of strontium and oxygen. So charges typically will have a larger influence.